Welcome back to fourth lecture of the boundary layer analysis, and we are going to start this lecture with problem number 5. The question says that the velocity profile for laminar boundary layer is given as small u by capital U is equal to 2y by delta minus y by delta whole square. Now we have to find an expression for boundary layer thickness delta and the wall shear stress. Okay. So what is given is u by capital U is equal to 2y by delta minus y by delta whole square. Therefore, the momentum thickness can be written as 0 to delta u by capital U 1 minus u by capital U dy. This is the definition, right, of momentum thickness. All right. So it is going to be 2y by delta minus y square by delta square into 1 minus 2y by delta plus y square by delta square dy whole dy, or the momentum thickness is going to be integral 0 to delta 2y by delta minus y square by delta square minus 4y square by delta square minus y to the power 4 by delta to the power 4 plus 4y cube by delta cube into dy. Okay. Or, and after integration and substituting the limits, the first term will give us delta minus delta by 3 minus 4 delta by 3 minus delta by 5, and the last term will give us delta. Therefore, theta is going to be 2 delta by 15. This is the momentum thickness. Okay. So we proceed to the next page where we are going to solve these questions further. So I am going to have a new. Okay. So we had got theta is equal to 2 delta by 15. Okay. Now from von Karman momentum integral equation, tau naught is equal to rho capital U square d theta by dx. Okay. So rho u square, and we put theta as here. So d dx of 2 delta by 15. Okay. Therefore tau naught is going to be 2 by 15 rho u square d delta by dx, and this is equation number 1. Also tau naught we know can be written as mu du by dy at y is equal to 0. And how do we get this? From Newton's law of viscosity. Okay. So velocity profile we already know. So if u by capital U was given in terms of y and delta, so we can, so from here we can go tau naught can be written as mu will mu, and now du by dy. Okay, so it will become 2 capital U by delta minus 2 U by delta square into y at y is equal to 0. So this will become mu, this term will go away, right? When we substitute, it will be 2, this is mu, so 2 U by delta. This is equation number 2. Equate 1 and erase 2 by 15 rho u square delta by dx is equal to 2 mu u by delta, right? So this is the equation that we get, and now to find delta, what we must do, we must simply integrate it. All right, so we will do this integration on the next page. So this integration will go like delta d delta is equal to 2 mu u, you just rearrange the terms, divided by 2 by 15 rho capital U square dx. Okay, so this will become delta d delta is equal to, we can cancel this one, I mean mu u, one u will get cancelled. Okay, this is mu, this is mu. Okay, into rho u dx, sorry, rho u square dx. Okay, or d delta, u gets cancelled, so it will be 15 mu by rho capital U dx, and then we can integrate 0 to delta, and this one will go from 0 to x, so 15 mu divided by rho capital mu dx, or after integrating it will become delta square by 2 is equal to 15 mu divided by rho u, sorry, this is capital U x plus c. This is the c is constant of integration. Okay, but how do we obtain c? We know to obtain c, we know that boundary layer thickness at leading edge is always 0. So at leading edge x is 0, right, and here delta is also 0. So if we substitute this in this equation, we get c is equal to 0. Okay, therefore we can simply say boundary layer thickness delta square by 2 is equal to 15 mu times x by rho u. All right. Okay, or just to simplify, what I am going to do, this left hand side will remain the same. So if you divide mu by rho, this becomes nu, right, and this u, multiply it with x on numerator and denominator as well, and this one is written as Reynolds number at a distance x. Alright, so I will just conclude here. Then delta square can be written as, we take 2 this side, that will be 30x square divided by REX, right? Or in other words, under root. So it 30 when done under root, it becomes 5.48x divided by under root REX. All right. So this is our first answer, boundary layer thickness. Now the second part, I will erase all ink. All right. So for second, we know that tau is equal to mu 2u by delta, right? That is what it came to. Mu. Now it's a matter of just the substitution. Okay. So tau naught is mu 2 capital U, delta is 5.48 x under root REX. Okay. So tau naught comes to be 0.365 mu capital U by x under root REX. So after that is found, you can express it in any form that you want. Okay. So this is the second part. It was a long question, but actually clearly indicated how we can use the van Karman momentum integral equation for finding the boundary layer thickness. Good. So now the last problem in this set is that for the previous problem, find the thickness of the boundary layer at the end of plate 1 meter long and 0.8 meter wide when placed in water flowing with the velocity of 150 millimeters per second. So the question, theoretically we have done, now we need to put in some values, and it says take the viscosity of water as 0.01 poise. Okay. So to solve this, we will go to the white screen again. As always, we will write given. So length is given as 1 meter, B is given as 0.8 meter, capital U is 150 millimeters per second, or we can write 150 into 10 to the power minus 3 meters per second. Okay. Mu is given as 0.01 poise, or in SI unit we can write 0.001 second per meter square. Okay. So what we have found out from the previous question, delta is 5.48 x divided by under root RE at x, Reynolds number. For laminar boundary layer, right? Because why laminar? Because we have used tau is equal to mu du dy, that is for the laminar boundary layer. At end of the plate, x is equal to 1 meter. End of plate. So Reynolds number at this position will be U x by nu, right, or rho u x by mu. So 1000 is the density of the water, 150 into 10 to the power minus 3 into x is 1 meter divided by mu is 10 to the power minus 3. So Reynolds number at x is going to be 1.5 into 10 to the power 5, and of course it is less than 5 into 10 to the power 5 means laminar. So our assumption was okay. Okay, so I will, before proceeding, all right. So delta by formula is 5.48 x divided by under root REX. So 5.48 into 1 divided by under root 15123 zeros, and that comes out to be 0.01415 meters. So the real values, I mean the numerical values, come 0.01415 meters. So this is the boundary layer thickness. Here we have calculated the boundary layer thickness in terms of the numerical values. Good. All right. So we will now proceed to the other topic. So we when we concluded before solving the problems, what we said was that the equation that equation is valid both for laminar and turbulent boundary layer. So first we study laminar boundary layer over a flat plate. Okay. So now this analysis is done by applying von Karman momentum integral equation, as it is common for both laminar and turbulent flow. The assumptions is that u is a function of eta. Eta is y by delta. Y is the distance above the plate and delta is the boundary layer thickness, and is not a function of x. So u is not a function of x but only a function of y, or if to be precise, y by delta. So what we do is we assume that u by capital U is a function of eta, and this is written as a plus b eta plus c eta square plus d eta cube. So how do we approach this problem? How many terms are there? 4 terms. How many unknowns? A, B, C, D. But fortunately we know that while doing those equations, von Karman momentum integration equation, we had 4 boundary conditions, if you remember. I will just briefly take you and show that. You see, so what were those boundary conditions? Very simple boundary conditions. So these were the 4 boundary conditions, if you remember. U at y is equal to 0 as 0, okay. Del square u by del y square at y is equal to 0 is also 0, and u at y is equal to delta is equal to u, and del u by del y is equal to at the boundary layer, right. The velocity gradient at the top of the boundary layer is 0, there is a free stream velocity, these two are 0. So now we apply this condition for also for laminar cases, okay. What we get, this function is a third order polynomial law. So what we get, so if you apply u at y is equal to 0 is 0, which will give us a is equal to 0. So if you put, if y is equal to 0, eta is 0, so a plus 0 plus 0 plus 0 is equal to 0, 0. If you apply second boundary condition, del square u by del square y, so you differentiate this f of eta twice, so this will become 0, this will become 0 on twice differentiation, this will give us 2c plus 6d eta is equal to 0. So when eta is equal to 0, this means c is equal to 0. So the first 2 conditions are going to give us a is equal to c is equal to 0, and substituting third and fourth, So, fourth one, the third one where we have to differentiate once will give us this condition. You can try this at home, and the fourth condition will give us d is equal to minus half. So, those 4 boundary conditions are used to solve for these value of a, b, c and d. Therefore, we can simply write that u by u by capital U, which is a free stream velocity, is given by 3 by 2 eta minus half eta cube. Now, if inserting the above in von Karman momentum integral equation, if we insert this, what do we get? So, tau w is written as rho u square d dx of, this is momentum thickness, right, theta, or in other words, you see this is f 1 minus f d eta, because if eta is equal to y by delta, so d eta is equal to dy by, all right. So, now the limit will change, because when y varies from 0 to delta, eta can vary from 0 to 1, right. So, eta is y by delta, when y is equal to 0 implies eta is equal to 0, and when y is equal to delta implies eta is equal to 1. So, this limit will change, okay, as shown. Or in other terms, what we can write is, so on integration and converting it into form of delta y by delta, this will give us tau w 0.139, rho u square remains rho u square. So, this value comes out to be 0.139, you can see that here, okay. Now, if we apply the Newton's law of viscosity at the boundary, why can we apply the Newton's law of viscosity? Because it is a laminar flow, okay. We did the same principle when we were solving the numerical problems. Or if you see du by dy at y is equal to 0, so you see, so du by dy at y is equal to 0, it is going to give us 3 by 2 mu into u by delta, okay. So, what do we do next? One way we have obtained Newton law of viscosity, and the other equation was equation number 11 here, right, because what we started with was the velocity profile here, all right. U by capital U is equal to a plus b eta plus c eta square, and in differentiating that we got this, and we are going to equate equation 11 and equation 12. This will give us delta d lambda d delta is equal to 10.79 v by u dx, and if we integrate this above equation, we can get the boundary layer thickness. Actually, the last problem that was there, problem number 5 and 6, was exactly the same problem that we solved. The way, I mean, the equations were different, but the way of solving was the same as this derivation. So, we can write delta square is equal to 10.79 v by u x, or delta square is equal to 10.79 nu by ux, right. So, what we did was we multiplied x and x upstairs, I mean denominator here also, okay. So, this becomes x square and this is Reynolds number. This is what exactly we did, or in other words, we get delta is equal to 4.64 x under root Reynolds number of x. Try to remember the question that we did, just finished in the last I mean before, at the beginning of this lecture. So, the above equation can be utilized for obtaining expressions for tau w and f drag, because we get the boundary layer thickness. and from the expression of Newton's law of viscosity we can obtain Tw, and F drag we can simply use how that we integrate tau W from 0 to L over the entire plate. So, this is the way that it is done. All right. Now, we will solve one problem. The problem is for the velocity profile for laminar boundary layer, u by capital U is equal to 3 by 2 y by delta minus half y by delta to the whole cube. Determine the shear stress and the drag force in terms of Reynolds number. We have done a similar problem, but we will do another one now to make it more clear. All right. So, first write what is given to us. So, u by capital U is equal to 3 by 2 y by delta minus half y by delta to the whole cube. For the given velocity profile, we have seen that delta came out to be 4.64x under root Reynolds number at x, right. This was the last derivation that we saw. Further, we have seen tau naught is equal to mu du by dy at y is equal to 0, correct. Implies tau naught is equal to 3 by 2 mu capital U by delta. This has already been discussed, right. Correct. So, delta we know from here, right. So, tau naught 3 by 2 mu u under root Rex 4.64x, or finally tau naught can be written as 0.323 mu capital U by x under root Rex. All right. Now, the second part is how do we find the drag force? Very simple, we have laid down the procedure. All right. All right. So, drag force Fd can be found out using integral 0 to L tau naught b dx, implies drag force Fd is equal to integral 0 to L 0.323 mu u by x under root Rex b dx. Here L is the length over which the drag is intended to be found. Okay. So, implies drag force integral 0 to L 0.323 mu u b x rho u x by mu to the power half dx. Okay. So implies FD actually can be written as, after integration, 0.323 mu capital U B rho to the power half, it will come out, capital U to the power half, it will come out, mu to the power half, it will come out, integral 0 to L x to the power minus half dx. All right. So after integrating and substituting the values of x from 0 to 1 or 0 to L, x goes from 0 to L, FD will be 0.323 into 2 into mu capital U B, alright, into under root mu UL by rho UL by mu. So this is the drag force. More importantly, it is the way that it has to be found. I mean, in your questions, you will be mostly given an objective question. If you know the way how to find it out, I mean, it will not be so tedious calculation. So I would like to end the lecture at this point in time, and we will go through some more concepts and some more questions in our next class. Thank you so much.